Okay, welcome back. This will be a fairly short lesson. We're looking at introducing something we call the equilibrium constant. You're going to hear me just refer to this as KEQ. So let's jump into our notes here. Okay, so what we need to look at here is how we write out, in this lesson, is how we write out this equilibrium constant. So we're going to look at an example here of this kind of general reaction here, this AB reaction forms C and D, this reaction right here. So this constant that we're going to talk about is going to give us a ratio of the product concentration to the reactant concentration. So remember that square brackets refers to the concentration. So what this is going to tell us is it's going to tell us kind of where this equilibrium lies, how far to the right or how far to the left. So when we talk about the amounts of the products and the amounts of the reactants relative to each other, if we can express these as concentration and give it as a ratio like this, then it's going to give us a measurement, a value, and a constant, giving us an idea of, do we have a high product concentration and very little reactants left over, or vice versa. And that's what this is going to help us understand. Okay, so first off, this K value is the first time we're seeing this in the course. The K is really just referring to a constant value. It's just a variable given to this constant. The little EQ subscript is referring to the reaction being at equilibrium. And so this KEQ value is going to give us a ratio of the products to the reactants for some reaction at a certain temperature, okay? So looking at this general reaction here, this is how we're going to calculate our KEQ value, okay? So notice what we've done is for each of the products on top, in our numerator here, we've got the concentration raised to the power of the exponent, okay? So it's always the concentration raised to the power of the coefficient in front of it in the reaction. So that's why we need the balanced reaction here. And then we multiply that by our next product, so the concentration of D raised to the power of that coefficient D in front of it. And this will be divided by, and then our numerator, pardon me, our denominator, we come up with the same way. Concentration of any reactants, so in this case A, raised to the power of coefficient A, multiplied by concentration of reactant B, raised to the power of B. So when we plug a bunch of numbers in there, we calculate it all out, we simplify that down, we get a value. That's going to be what we call our KEQ value. So this lesson will kind of just focus on how we write out this reaction, because it is kind of strange seeing it for the first time. Before we write out the actual equations, let's just think about what this value, this constant, actually helps us understand. When we have a KEQ, an equilibrium constant value, which is much greater than 1, which is what we're saying here. So in other words, we're saying that KEQ is, very large, relatively speaking. We have a reaction or an equilibrium that favors the products, is what we're going to see. So we favor the products. So what that tells me is, and use some simple math here, if our ratio comes from the product concentration divided by the reactant concentration, well, how does this fraction give us a large number, a number much larger than 1? Well, it means that the number on top must be a lot larger than the number on bottom. So that means that my product concentration is much larger than my reactant concentration. So we say that this equilibrium favors the product side. That's where most of our material lies in that phase. We also say that this equilibrium lies very far to the right, which is to the product side. So there's a few ways we can describe that. In the bottom, if your KEQ value, if KEQ is very small, so this is saying much less than 1, then we have a reaction that favors the opposite direction. Again, how does a fraction like this, how does products divided by reactants give us, let's just pick a number, let's say like 0.001. How do we get such a small decimal there? Well, we must have a very small amount of products compared to a very large number of reactants in order to give a number less than 1 like that. So that just favors the opposite side. So we have a high reactant concentration compared to a relatively small product concentration. The opposite is how we describe that. We say that this equilibrium lies very far to the reactant side. It favors the reactants, or it lies very far to the left. So it helps us understand the direction in which this kind of balance is lying here. When we have KEQ values that are between, these kind of very large or very small numbers, then really we just have a lot of both. So, think about, what does a KEQ value of exactly 1 tell you? Well, really it tells you that you have products equaling reactants in order for that division to give you a value of 1. Okay, so if you're anywhere kind of remotely close to 1, so we talk about things like, anywhere from 1,000th up to 1,000, you have a significant amount of both reactants and products. You might lie a little bit further to one side, but not drastically, like some of these much larger or much smaller numbers. So here's a visual kind of describing the same thing as the last slide. Okay, so when you have a KEQ value, now this is saying anywhere from 10 to the negative 3 would be like 1,000th, all the way up to 1,000, right? So that's when we divide our product concentration by our reactant concentration. So if we actually complete that calculation, if we're getting a KEQ value in this range, we've got a pretty decent amount of both reactants compared to products, okay? If we move to the right to get that very large KEQ value, we're talking like 1,000 or larger, and it could be much larger, then again, visually, this just shows us what we had on the last slide. You're mostly products with a very small amount of reactants compared to those. Going the opposite direction, the opposite's true. To get that very small KEQ value, you must be mostly reactants compared to a very small amount of products. So it all comes down to this ratio at the top here, how we actually calculate KEQ. Now, what does that number tell us? So don't worry about specific numbers yet, but just look at the general size of them and understand, and try to start understanding what that general size helps us understand, okay? So for example, if I had 2 reactions, 2 different ones, and one of them had a KEQ value of 1 times 10 to the negative 5, and one of them was 1 times 10 to the 3, well, we have one that's very, very small, one that's definitely larger, okay? So which of these equilibriums would you say lies further to the reactant side or further to the product side? So this one being smaller lies further to the left, the reactant side, like that one. This one being larger would lie further to the right, the product side. So it's just kind of a comparison is what it helps us do at this point in time. A few things before we stop about KEQ. Please note that KEQ has no units. It's just a constant value. So even though we're dividing concentrations by concentrations, and you might later on when we do some calculations, you might see things not cancel out perfectly. They have no units, just a value, a number. So you're going to get things like 0.12, and that's it, just as an example. Okay. Don't try and put any units attached to it. Make sure you are using molar concentrations, okay? This little note about an ice table, we'll see an example of that in our next lesson, so don't worry about that. But just make sure we use actual concentrations in that calculation. So we can't use, grams or moles, anything like that. It's got to be molarities in there, okay? The third and fourth points are really important, and that is gases and things in solution, aqueous species, are used in that formula, that calculation, and that's because they have concentrations. So just be very careful that solids and pure liquids have no place in that calculation. We don't even touch them, don't even use them, and that's because their concentrations are already constant. So, I mean, we could go into that in class if we want, but basically ignore those in your KEQ calculations for solids and pure liquids. Leave them out of there. The last couple points, also really important. Things that we know might affect an equilibrium, like pressure, concentrations, catalysts, we know don't affect an equilibrium, but things like changing the pressure or volume and concentration from Le Chatelier's lesson, these don't actually change. They have no effect on the KEQ value, okay? And that can throw some people off sometimes. So when we have an equilibrium constant that comes from our product divided by our reactant concentrations, when we, let's say, change the concentration or the pressure, we do have a shift in an equilibrium. So they shift the equilibrium, but they do not change the KEQ value. And that's something we can go over if you like, if you care to kind of think about it that deep, or just remember that they do not affect the equilibrium constant at this point. Okay? The last point, because one thing we didn't mention is temperature. Temperature will affect the KEQ value. Okay, so temperature will shift in equilibrium. We know that from our last lesson, but it will also affect the equilibrium value. We can look at that with some examples together. So let's do just a couple examples here in terms of showing how we actually write out these equations. We don't need to calculate anything now. So first step would be always start with your balanced equation. Sometimes you're given it, sometimes you're not. So in this case, we've got our balanced equation, and we just want to practice how do we come up with this KEQ formula, okay? So product concentrations divided by reactant concentrations. It's kind of the simple version. So we have our concentrations raised to the power of the coefficient from the equation. And that's how we're going to be inserting them into that respective place. So we've got, for the first one, my KEQ would be concentration of my ammonia. That's my product. And that's going to be squared because of that coefficient 2. Okay, that's my only product. And I included that because it's a gas. So that gets included in the formula. Divided by, and then on the bottom, I've got two reactants. Both are gases, so they both get included. So concentration of nitrogen. Now the coefficient here is 1. So I've got an exponent of 1 on that one. Don't need to show that. Multiplied by the concentration of hydrogen gas raised to the power of 3. So that's cubed because of that coefficient 3 in the equation. That's it for now. Our next lesson, we'll certainly look at how we do some calculations involving that. Okay. Second one, I don't have phases here. I should. So let's throw in our gas phases there. Now notice this is just the reverse of the reaction above. My KEQ, whoops, didn't show up. My KEQ formula for this one. So it's really common for people to do this backwards. Please always remember it's products on top, reactants on bottom. Okay, so my products here. So I've got already my balanced equation. So I'm going to have concentration of my nitrogen, N2. Coefficient here is 1. So that's just raised to the power 1. Multiplied by concentration of hydrogen gas, H2. And because of that coefficient 3, that value will be cubed. Divide that by my reactants. I just have my ammonia, NH3. So concentration ammonia, and because of that coefficient 2, that value will be squared. So there's my KEQ equation, okay? So because these reactions were the reverse of each other, it hopefully is no surprise that these are the inverse of each other, just flipped around. So a couple examples here, be really careful. That point we made about solids and liquids having constant concentration. These examples will show you why that matters. So KEQ, products concentration divided by reactant concentration. Include aqueous and gases. Do not include solids or pure liquids. So this example will highlight how that will definitely change how your equation looks. So we still start with our products. So let's look at our products. This first product here, solid, don't even touch it, okay? My second product, my carbon dioxide gas, that'll get included, okay? So if we look on our formula here, oops, let's get rid of that. I've got my concentration of my carbon dioxide divided by, now I look at my reactant side. My reactant side, I've just got my calcium carbonate, which is a solid. So what we're going to do, I mean, what you could do if you want is you could throw some ones in for the constant concentration for those solids, but obviously you're not going to leave your formula like that with a 1 over 1, okay? This formula really just simplifies to this, okay? It happens to be the only gas species there that gets included, and that's it. So let's try this one, a little bit bigger of an equation, reaction. So let's try our, let's try to build our equation. So let's look on the product side. Get rid of that. Let's look on the, pardon me, product side here. Okay, so first product is a solid. Will it get included in this equation? No. Second product, water, pure water, liquid. Will it get included in this formula? No. Third product, carbon dioxide gas. That's a gas, so it does have a concentration, it gets included. So concentration CO2. Our equation was balanced, so the coefficient's 1. My exponent there is 1. On the bottom of that, look at your reactants. So first reactant, my calcium carbonate is a solid, does not get included in this calculation. My second reactant is a gas, so I include its concentration, and the coefficient there was 2, so I need to square that value. So there's our finished formula or equation to calculate the KEQ value for that reaction. Okay, this section we'll stop there and we'll look at some calculations, a little bit of practice building this equation on its own.